Hi, welcome to my channel Husni Firmansyah. Here, I will share my experience solving one of HackerRank's problems called determining DNA health. This is a hard level problem with a success rate below 40%. If you're a skilled developer, I recommend you try solving this problem. Will it be a challenge for you? If you've already solved it, please comment below. Your solution might be different from mine. If you want to learn more about the problem, you can visit HackerRank.com and type DNA health in the search bar. A pop-up will appear. Click on the problem titled Determining DNA health. Alright, let's explore what the problem is. Here's the problem. It's a long description with a lot of explanation. Don't worry, I'll break it down with a simple example. Given some genes and their corresponding values in a zero-base index array, there are 6 genes with their respective values. Gene A has a value of 1, Gene B has values 2 and 6, Gene C has a value of 3, Gene AA has a value of 4, and the last one, Gene D, has a value of 5. We are also given some DNA strands along with starting and ending indices to calculate the DNA health from each strand. For example, there are 3 DNA strands, each with its own first and last index. The first strand is CAAAB with the first index of 1 and the last index of 5. The second strand is XYZ with the first index of 0 and the last index of 4. The third strand is BCDYBC with the first index of 2 and the last index of 4. So the problem is to calculate the DNA health of each strand and then print the minimum and maximum DNA health. For example, the DNA strand CAAAB has a DNA health value of 19. This comes from Gene C with a value of 3, Gene AA with a value of 8 from 2 occurrences of Gene AA, each valued at 4, and Gene B with a total value of 8, 2 plus 6. Since Gene B is within the range of the first and last indices 1 and 5. For the second strand XYZ, the DNA health is 0, because none of the genes are present in the strand. For the third strand BCDYBC, the DNA health is 11. This comes from Gene C, which appears twice with a total value of 6, 2 times the value of 3, and Gene D with a value of 5. Gene B is found at 0 because the range of the strand is from the first index 2 to the last index 4, while Gene B's indices are 1 and 5. After calculating the DNA health for all the strands, the minimum health is 0 from the second strand and the maximum health is 19 from the first strand. Therefore, the result is 0, 19. Okay, after understanding the problem, you might ask, is this really a hard level problem? I think the solution is straightforward. We just look through all the strands, reverse each one, and compare it with the genes. If there's a match and it's within the specific range, we calculate the health. After calculating the health for each strand, we look again to determine the minimum and maximum health. If you think about it that way, I might agree with you. It seems like a simple problem, not a hard level one. But unfortunately, the challenge is more complex. The number of genes and strands can each be as large as 100,000, and the total number of characters can reach 2 million. If you use the approach we discussed earlier, it will result in a TLE, time limit exceeded, due to the time complexity of big O of M times N, where M is the total number of genes and N is the total number of strands. So, what's the solution? Okay, after this, I will explain how to solve the problem. If you want to try solving it yourself first, feel free to pause or stop the video. and come back to compare your solution with mine. But it's perfectly fine if you'd like to continue watching the video right now. So let's move on to the solution. Here's the solution. To solve the problem without encountering a TLE, I need to use algorithms that can achieve at least big O of m log n or even big O of n type complexity. The algorithms I will use are as follows. First, I will use a trie to restructure the genes and their values. Second, I will use a suffix tree to restructure each thread. Okay, I will start by explaining the trie of genes. The trie consists of several nodes, with the root node at the top. The root node has child nodes, node A for gene A, node B for gene B, node C for gene C, and node D for gene D. Node A has a child node A representing gene AA. Notice that some nodes have values that represent the index and value of the gene. For example, node A has an index of 0 and a value of 1. The node A beneath it representing gene AA has an index of 3 and a value of 4. The same applies to the other nodes, like nodes B, C, and D. Okay, let's continue with the explanation of the suffix tree. Each DNA strain will be restructured into a suffix tree. For example, take the strain CAAAB. After restructuring, it will look like this. It resembles a trie, right? That's because the suffix tree is essentially a compressed trie. The strand CAAB has 5 suffixes: CAAAB, AAAB, AAB, AB, and B. The suffix tree contains nodes starting from the root node at the top, followed by the nodes X and Y. There are edges represented by arrows between nodes and leaves. The number of leaves represents the number of times a prefix appears. For example, the prefix CA has 1 leaf, meaning it occurs once in the strand. Another example is the prefix A, which has 3 leaves, showing that A occurs 3 times in the strand. Finally, let's take one more example. The prefix AA has 2 leaves, representing that AA appears 2 times in the strand. The number of leaves for a prefix will later represent how many times a gene appears in the strand. To avoid the suffix tree, I will use Acquaintance algorithm, as it constructs the tree with a time and space complexity of big O of n. A suffix tree is used to find genes in the strand. Once found, I can calculate the health. The details are as follows. Traverse the suffix tree using DFS. Then first search while simultaneously checking with the trie to see if any genes match. If a gene is found, calculate its health and multiply it by the number of leaves on that edge. The number of leaves represents the number of times the gene appears in the strand. For example, to calculate the health of the strand CAAAB, we start by traversing the suffix tree from the root node at the top using the FS, then first search. Starting from the root, we move along the edge labeled CAAAB. Let's check. Each character on that edge. Is the character C found in the trie of genes? Yes, it is. Next, we calculate the health for C. C has an index of 2 in the genes. First, we check if this index falls within the range of the strand's first and last index. Yes, it does. What's the value of C? The value is 3. We then check the number of leaves on the current edge. The number of leaves is 1, so we multiply 3 by 1, resulting in a health value of 3. After finding and calculating the health for gene C, the strand's current health is 3. Next, we continue traversing the suffix tree, but before moving forward, let's check the trie. Are there any nodes beneath node C? No, there aren't. So we proceed with another edge. Now let's traverse the edge labeled A. Is A found in the trie? Yes, it is. What's its index? The index is 0. Let's check if the index is within the range of the strength's first and last index. No, it's not. So we skip calculating hold for gene A and return 0 for this case. Let's continue. After the first A, we move to the next A on the edge. Is AA in the track? Yes, it is. What's the index? The index is 3, which represents gene AA. Now check if this index falls within the range of the first and last index of the string 1 to 5. Yes, it does. What's its value of AA? The value is 4. How many leaves are there in the suffix 3 for this age? There are 2 leaves. So we multiply 4 by 2, giving us 8. We then add this to the previous hold value of 3. Now 3 plus 8 equals 11. The current hold of the string is 11. Let's continue traversing the suffix 3. Since there are no more nodes after A, we move to another edge. The next edge is B. Is B found in the track? Yes, it is. So we calculate its hold. B has a total value of 8 from 2 plus 6, as both values are valid within the range of the strength's first and last index. We then add this value to the previous hold of 11. Now 11 plus 8 equals 19. Finally, we continue traversing, but since there are no nodes beneath B and no further edges to traverse, the process stops. The total hold of the strength CAAB is 19. To calculate the health for the other strands, the process is the same. After calculating the health of the strand XYZ will be 0, and the health of the strand BCDYBC will be 11. Taking the minimum and maximum health values, we get a minimum of 0 and a maximum of 19. Therefore, the result is 0, 19. In conclusion, to solve this problem, first, build a tree from the genes and their values. Second, construct a suffix tree for each strain using a Kuhn's algorithm. Third, traverse the suffix tree while simultaneously checking the tree for gene matches and calculating the health. Fourth, find the minimum and maximum health values from those strains and print them. In this video, I won't go into the details of the tree suffix tree Kuhn's algorithm or DFS. You can find explanations for these algorithms on YouTube or by joining classcoding.id, where they will be part of my class materials. Before I move on to the coding, if you're currently watching on a mobile phone, I suggest switching to laptop or desktop for a clearer view of the code. Alright, let's move on to the coding. Okay, that's all from my solution to the determining DNA health problem. If you want to learn how to solve problems like this, visit classcoding.id and join. I will guide you step by step from the basics to advanced. Thanks for watching my video. If you enjoyed it, please give it a thumbs up below. If you'd like to see more videos like this, don't forget to subscribe. And if you have a different solution to this problem, feel free to share it in the comments. See you in the next video. Have a great day and bye.